So today we are talking about compressing data. So there is a lot of data in the world around us. As our world becomes increasingly computerized, as we get more and more computers running stuff, digital data is constantly being created and stored, and we need some way to keep track of all of it. Now, physical media, the ways that we can actually physically store our data, is always improving. There are more efficient ways to store digital data being developed all the time. We used to have to use punch cards, little slips of paper, which we would punch holes in to store data. Later, we would get floppy disks, CDs, DVDs, Blu-ray disks. Now we have hard drives, solid state drives, and we have even smaller and smaller pieces of physical media to store larger and larger amounts of data, which is really, really good. But as we have more and more data, we need to be able to store, we need to have more than just hardware solutions to solve this problem of increasing data. We need to have some software method to shrink down our data so that it takes up less space. And that's where compression comes in. Data compression is the process of encoding information using fewer bits than were used in the original representation. So if we can store some information using less space than originally, we are going to be compressing that data down. And there's all kinds of different algorithms for compressing information. And so we use those to compress that information down, to use less bits so we can store it. And then we're going to, after we've compressed it, if we want to access that data later, we're going to decompress that information to fully, properly view it. So if we look at this little illustration, we've got this sequence of binary values. We're going to run some compression function on it to get a much smaller number of bits. And then we can use a decompression function to get that same sequence of ones and zeros. Lossless compression is what happens when we are able to compress information and then later decompress it to get the exact same value. And this is pretty valuable because it means that we are not losing any information in that space-saving process. Tomorrow we'll talk about lossy compression, in which sometimes we can lose information when we compress. Sometimes it doesn't matter. We'll get into it tomorrow. But there are all kinds of different algorithms for doing all kinds of different data compressions. Just about every piece of digital data that we are working with is going to be compressed before we store or send it, which makes saving space really helpful, which is good because we're saving space. And it's going to make working with that data a lot faster because we don't have to worry about as many bits when we are storing it or sending it. Movies, music, images, text, all these things are compressed when we store them digitally. So some reasons why compression is useful. We are saving storage space, which is always great. The more data we can store on a hard drive, the better. So if we can compress the stuff that we have into a smaller area, we can put more things on that drive. And if I have a smaller piece of information, it's going to save me both time and bandwidth when I'm sending that information to someone else via the internet. When there's less bits to be sent, the sending process happens a lot faster. And another great reason to do compression is that we're trading off storage, which in computer terms is expensive and slow. We're going to trade storage for computing power, which is much, much cheaper and much faster. The CPU is on your computer is going to access your information much more quickly than having to go into your hard drive and access it. So if our data is compressed, we can run some decompression algorithm to get the data we need rather than having to store all of our raw data on a hard drive. So as an example of this, our cell phones really don't have the memory capacity to store the raw footage for a movie or a full-length feature film. Those are usually hundreds of gigabytes large, which is a little ridiculous. What our phones do have is the computational power to decompress a movie, which is, once it's been compressed, it's going to be much, much, much smaller. So we can decompress that file to view it whenever we want to actually see it. So we don't need to store all of the expensive large files because we can just decompress them when we need them. So a general idea of how compression is going to work. Compression works by finding repeated patterns in the data and then replacing those patterns with some placeholder that's going to take up less space than that pattern. And patterns are actually super common in things like text and video and in images. So for a very, very basic example, let's say I have 100 pixels and they're all the exact same color. So they all have the exact same RGB value. One RGB value for a pixel is going to be 24 bits because we have 8 bits for each of the R, G, and B. So 8 plus 8 plus 8, that's 24. So we have 24 bits per pixel in this little picture. So we have 100 bits, 24 bits per pixel. That's 2,400 bits, roughly. Not roughly, that's how math works. If I wanted to compress this, since I'm repeating that one pixel over and over again, every single pixel has the exact same RGB code. I can just say I have one pixel, one purple pixel. I can store the RGB value for that one pixel. And I can just say, I have that pixel 100 times. Usually we're going to store numbers in 32 bits. So we're going to store the RGB value for a single pixel. And we're going to store how many times we're repeating that pixel, which is going to total up when we add 24 to 32. We can store that same information in 56 bits rather than 2,400. We've saved a whole lot of space by using that compression system, saying I'm repeating this pixel that many times rather than storing the information for every single pixel all by itself. One text compression algorithm that we can work with is called run length encoding. And this algorithm is going to work well when there's a string with a character that's repeated many times over and over again. So let's say I have the string, hey, hi. What I can do is for each sequence of characters, I can say how many times that character appears in a row. So if we start at the beginning, we have the letter H, and that's only going to appear one time. So we're going to start our value, our compression value, with H1. The next thing we see is the letter E repeated a bunch of times. So we can count 1, 2, 3, 4, 5, 6, 7, 8, 9. We see 9 E's. So we put an E and then the number 9 in our compression, saying when you are going to read this, you're going to put 9 E's in the actual value. We see 1 Y, so we say Y1. We see a single H, H1. And then we see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 I's. So we put I11, which is going to give us this compressed version of that string. Now, this compression algorithm really works best when we have a whole bunch of repeated characters. If we have a whole bunch of single characters, where we might actually create a longer compressed string than our original string, which is not really ideal. But in this scenario, if we look at how many bits were being used in our original, we have 22 characters total, and each character can be stored in 8 bits. We talked about how we store characters with ASCII, so each character uses 8 bits. So the total number of bits being used here is 176. When we compress it, we are gonna have only 11 characters, and when we multiply that by our 8 bits per character, we're gonna get 88 bits, which is half as large. We've compressed this down by half the size, or compressed it down to half the size. If I want to decompress, we can just follow the pattern in our compressed version. So we have H1, we have 1 of H. E9, we're going to add 9 E's. We have Y1, H1. And then I11, we're going to have 11 I's in a row, which those two strings, they're different fonts, but they match. They are in the same sequence of characters. Our compression algorithm is lossless. If we want to measure how much space is being saved, we can do this little calculation. The space savings is equal to 1 minus the size of the compressed thing divided by the size of the original thing multiplied by 100. So we're going to get some percent. So if we look at our encoding here, 1 minus 88 over 176 times 100, that is a space savings of 50%, which is a pretty good encoding. It's pretty good space savings. Our compressed data, 50% smaller. We've decreased the size by half, which is really, really good. Now, run length encoding is just one example of a compression algorithm. All kinds of different algorithms exist for compressing all kinds of different data. JPEG is a common image compression format. Zip is a file format for compressing large amounts of text. And in order for compression algorithms to work well, they need to have a matching decompression algorithm to reverse the compression process. And our computers use different file formats to keep track of what kind of compression is being used to store the data in that file. So if my computer sees a zip file, it knows it's going to need to use a specific algorithm to unencode all the information within that file. If it sees a JPEG, same thing. It needs to use the exact correct algorithm to unencode all the things in that file. So as an example, let me pull up a folder real quick. So I have this folder on my computer. There we go. I have a folder on my computer. I've got a cats.jpg. So if I open this up, see a picture of my 2 cats. They're very cute. And I have a text document, a .txt, called my text doc. That says the word hey in ASCII art. If I change the file type of one of these, let's say I rename this and I change the thing after the dot, I change that JPEG to a TXT, I'm going to get a little warning saying, hey, if you change that file extension, the file might be unusable. I'm going to say yes. Now when I try to open cats.txt, it's trying to interpret all of the bits in that file as it would a TXT file, which is really not what we're looking for. Let me actually share my whole screen so that we can see this. So if I try to open it as a TXT, all of the bits are now unreadable because this is not the correct way to interpret that information. this information is intended to be read as a JPEG, but if I change it to a TXT, I'm going to break stuff. So if I rename this back to a JPEG, I can open it up, and it is still a picture of the cats because it's still the same data, but now I'm interpreting it in the correct way. The same thing is true with my TXT. If I rename this to change the type to a JPEG, now the little symbol changed, but if I try to open it, it's not supported because the data in that file wasn't meant to be interpreted as a JPEG. It's meant to be interpreted as a .txt. So it works when I open it as a TXT, but not when I open it as a JPEG. Does that all make sense?